In this section, we are going to talk about power and the induced torque in synchronous generators. As we know, this synchronous generator converts mechanical power to three-phase electrical power, and the source of the mechanical power, which is called the prime mover, can be of different types. It can be a diesel engine, a steam turbine, a water turbine, or any other devices that can supply this mechanical power to the synchronous generator. In general, the requirement is that the prime mover speed should be almost constant. If it's not constant, if it keeps changing, then the resulting power system's output frequency will also keep changing, which is in general not good for the application. Okay. And not all the mechanical power going into the synchronous generator will be converted 100% into electrical power. Some of them will not be converted and they will become losses, as we will see in the following slides. Okay, on this slide we've got the diagram of the power flow of this synchronous generator, and the input power is equal to the applied torque times the omega m. The applied torque is the torque supplied by the prime mover into the generator. And then from the power flow diagram we can clearly see that the output power, which is this one here, is not the same as the input power. Okay, and the difference between these two powers is due to losses that happen in the system, and we have learned before that there are different types of losses, including mechanical, electrical, and magnetic losses. And in between these two powers we have this converted power, which is the power that is being converted from the mechanical into electrical. And the level or the amount of power of this converted power is again in between. It's less than the input power, but it's higher than the output power. Okay, this converted power is equal to the input power minus these three losses. So if you subtract these three losses from the input power, then you will get the converted power. And to get the output power, you can subtract the copper losses from the converted power to get the output power. Okay, and another thing that I need to highlight here is if you look at the equation for the input power is equal to the applied torque times omega m, while for the converted power is the induced torque times omega m. The induced torque for synchronous generator is also called as counter torque. So if in a question you find the term counter torque is referring to this induced torque. Okay, both of these two powers, the input and the converted powers, have got the term omega m, which means that the speed is the same for both, and logically they cannot be different because we are talking about one machine, and also it's coupled to directly coupled to the prime mover, so all the speeds will be the same. However, the torques are different, and again this is because of the losses, so the induced torque will be lower than the applied torque. Okay, and then if you look at the second bullet point here, the converted power is equal to induced torque into omega m, yeah, which is, this is the mechanical power, and is also equals to this expression here, 3 EA times IA cos gamma, gamma being the angle between EA and IA. So this is actually the induced voltage and then the induced current in the armature circuit, and the power in the armature circuit is equal to the mechanical power being converted. Okay, and then then after it's converted to electrical power, before we get to the output stage, there is another losses which we mentioned before as the copper losses. This is due to the resistance, internal resistance in the. Okay, on this slide we just see the equations for the real power and the reactive powers, stated both in line and phase quantities. Okay. Now we'd like to derive an equation that is very useful for predicting the output power, and the equation that we derive on the slides will also be used to predict the torque that we will have a look at the next slide after this. Okay, if the armature or the stator resistance RA is ignored, which is a valid assumption, yeah, since RA is a lot smaller than the synchronous reactance, then we can get a useful equation for predicting the output power. Okay, if we look at the equivalent circuit here, then when we ignore the RA, so it means RA will no longer be there, so we'll just have a line in here. Okay, and then if we write down the KVL from these equivalent circuits, what we are going to have is that EA is equal to V pi plus JXSIA. Yeah. So now then we can draw the phasor diagram. This is so the total of V pi plus JXSIA give you EA. So here is the V pi and this is the JXSIA vector, and the total of these two will give us this EA. Yeah, that's EA. Okay. Now from the previous slide we also learned that P out, the output power, is equal to 3 V pi times IA times cos theta. Yeah, right. From this the phasor diagram, we can find the equivalent of IA cos theta here. Yeah. How do you find this IA cos theta? Theta is the angle, yeah, between IA and V pi. If you look on the left hand side, yeah, this is theta, but theta is also this angle here. Yeah, if you look at it's the angle between JXSIA and the vertical line BC. Yeah, that's also theta. You can use the trigonometry to find this this angle will be the same as this angle. Okay, and because this is theta, so and we know the length of this side, then we can derive the distance between B and C, yeah, which is XS IA cos theta, yeah, that's BC equal to, okay, yeah, it's XS, yeah, not, let me just write it, okay, XS IA cos theta, right, and then you got XSIA cos theta. But now if you look at this triangle, the big triangle here, yeah, triangle from the origin to B and then to C, then also you can derive BC is also equals to EA sine delta, yeah? Delta is this angle here. Again, if you look at the left hand side, that is delta, which is the angle between EA and V pi. Okay, so we have two equations for BC, yeah, which is XSIA cos theta and EA sine delta. So it means that XSIA cos theta is equal to EA sine delta, yeah? And therefore you can derive that IA cos theta is equals to EA sine delta over XS, yeah? And really, this is what we've got. If you look at the blue box, the light blue box, this is the equations that we have derived just now, yeah? IA cos theta equals to EA sine delta over XS, yeah? Okay, and we've seen that we use the phasor diagram and some trigonometry to work out this equation. Now after we've got this equation, then we can if you look at the equation of the output power, then you can replace this IA cos theta. You can replace this IA cos theta with this, yeah? So you will find that the P out equals to 3 V pi times EA sine delta over XS, which is exactly what we have here, yeah, the next equation down. Okay, now the converted power is equal to the output power. Why is it so? Because we had the assumption before that we are ignoring the resistance RA, yeah? We are ignoring the resistance RA, so there is no armature resistance. Now if we go back, if you look at the power flow diagram quickly, now because we are ignoring the RA, it means there is no copper losses, yeah? And if there is no copper losses, it means that the converted power will be equal to the output power, yeah? And hence this equation here. Okay, right. So this equation is a very useful equation if you want to predict what is the output power, and we can get it by measuring the electrical quantities that we have in this equation. Okay, and this equation shows output power depends on the angle delta between V pi and EA, and this angle delta is also known as torque angle. Okay. And if we look at the equation, the maximum power can theoretically reach if the delta is equal to 90 degrees, so sine delta gives you 1, and it gives the maximum power of 3v pi EA over xs. That's again when delta is equal to 90 degrees. However, in reality, the manufacturers will specify that the full load torque angle is between 20 degrees to 30 degrees only. Right, okay, on this slide we want to get the equation to allow us to predict the induced torque by using electrical terms. Previously we had these equations that the induced torque can be calculated by if we know the values of some magnetic field densities, the BR and BS. Now we can also derive the value of or calculate the value of the induced torque by using another equation. Starting from these two equations here, that this is the equation for the converted power that we derived on the previous slide, and this is another equation for the converted power. I mean, the top one is more an approximation, but the bottom one is the actual equation for the converted power, induced torque times omega m. Now from these two equations you can write that this value will be equal to this, okay, and then you can rearrange the equations to solve for the induced torque, which is equals to the converted power over omega m from this, and then the converted power you can substitute by this, and you should get this expression here for the induced torque. And apart from this, the omega m is the speed, which is a common parameter in this system for both the prime mover and the generator. The other parameters that we need to that we have in this expression, they are all the electrical quantities, and therefore we can predict the value of the torque if we can measure all these parameters, which is a useful tool to know. Okay, now in this section we are going to look at the process of getting the values for the parameters that we use in the model or in the equivalent circuit of the synchronous generators. Yes, this process is very important. Otherwise, without this process, we don't know what are the values, of the parameters, and therefore the model is not going to be of any use for us. To give us more illustration of what it is actually, let's say, for example, to make it a bit simple, if somebody gives you a resistor and you don't know what's the value of it, you don't know what is the resistance of it, then assuming that you don't have any ammeter, you can find the value of the resistance by connecting it to a power supply, a DC power supply. Then you can measure the current, and then you will be able to derive the resistance of that resistor. So let's say if this is your resistor, you connect it to a power supply, okay, and then you measure the voltage, and also measure the current. Then you can derive the value of the resistance will be V over I, the current. So we are going to do something similar like this, but we apply it to this synchronous generator. Okay, if you look at the equivalent circuit of this synchronous generator, there are three quantities that we must determine in order for us to be able to use the model. So the first one is the relationship between the field current and the flux, and therefore the field current IF and the internal generated voltage EA, which is the link between the field circuit and the armature circuit. So we need to have this relationship. Okay, and then the second one is the synchronous reactance XS, which is for this. Okay, and finally we also need the armature resistance RA. Okay, so once we know these three values, these three pieces of information, then we'll be able to use the model. And to find these quantities, we need to do this open circuit test, short circuit test, and also applying a DC voltage to the machine's winding when it's stationary. And we will look at these processes one by one in the following slides. Okay, the first test that we need to do is the open circuit test, which is done to let us find the relationship between the internal generated voltage and the field current IF, which is quite straightforward. First of all, we let the generator to run at its rated speed, and all the terminals are disconnected. This is why this test is called open circuit test, because all the terminals are disconnected from any load. Okay, and then we start with the field current being set to 0. Okay. And next we increase the field current in steps, and while we are doing that, we measure and record the terminal voltage or the phase voltage. Okay, and in this case, the phase voltage will be equal to the internal generated voltage EA, because no load is connected, and therefore the armature current is 0, and therefore there is no voltage drops across the reactance nor across the resistance. Again, you can look at the equivalent circuit to see what it means. And therefore we will have a set of values of the IF and EA, and these sets of values will allow us to create the plot as shown here. This is called the open circuit characteristic. This plot is called open circuit characteristic. Okay, and again, you can get this value by keep increasing the value of IF and record the values of EA that is measured. Okay, so this is the first test, and again, the function is to determine the relationship between the field current and the internal generated voltage EA. Okay, now it comes to the next test, the second one, which is the short circuit test. This test is done or conducted to allow us to determine the synchronous reactance XS. However, to derive this value of XS, actually we need the information or the data from both open circuit test and the short circuit test, as we will see later. Okay, how do we conduct this short circuit test? Okay, similar to the previous test, we let the generator to rotate at the rated speed. Yeah? But now all the terminals are short circuited, yeah, through ammeters. Basically they are short circuited, but we use ammeters in this path to allow us to measure the armature current IA. Okay, and then to start with, the field current is set to 0, yeah, just like in the previous test. And then we record the armature current. Now the field current is increased again in steps, and while we do that, we measure and record the armature current by using the ammeter. Okay, and then again the sets of values of IF and IA. From this set of values, we can create the plot as shown in the yellow box, yeah, and this plot is called as short circuit characteristics, or SCC, yeah, which is the plot of IA against IF. Okay, once we've got these two plots, the open circuit characteristics and the short circuit characteristics, then we should be able to derive the value of XS, or the synchronous reactance. How do we do that? So first, we need to know that this value depends on IF, so we need to determine what is the IF is first. Yeah, what is the value of IF? Yeah, for example, if you look at the plot, yeah, let's say this is IF, and then from that value of IF, yeah, you can determine the value of EA from the OCC. If you look at the OCC, which is the plot of EA against IF, so if you know IF, you can determine the value of EA by using that OCC. Yeah, and then secondly, you can derive the value of the armature current, yeah, short circuit, from the SCC. Yeah, for example, in this plot here, you can then determine the value of the armature current from the plot, right? And then finally you can calculate XS. It can be approximated by using this approximation, that it's approximately equal to EA over IA from the short circuit. Yeah? Why is this so? Because the actual relationships come from this, yeah, that ZS, which is the total of this RA and synchronous reactance, yeah, is equal to the voltage divided by current. Okay. However, because XS is significantly larger than RA, then you can ignore this RA squared term, and therefore you'll end up with just simply XS, yeah, which is approximately equal to this term here, EA over IA. Okay. Okay. A drawback of this method is that the internal generated voltage EA is measured during the OCC, where the machine can be partially saturated, yeah, for large field currents, or IF. Okay, again, when we did the OCC, the machine can be partially saturated. However, when we do SCC, yeah, when we measure IA in the SCC, the core is unsaturated, yeah, because we only apply a very low current in here. Right. Therefore, this approach, yeah, to determine the value of the synchronous reactance, or XS, is accurate only for the unsaturated region. Yeah. Okay, so which is within this area here, that if you look at the graph, be only accurate in this region here. And where you can see as well the value of XS, yeah, is actually constant. As you can see, so if you want to get this XS value for this, we can use any value of IF that is falling within this region here, right? Okay, now what about in the saturated region? The approximate value of the XS varies with the degree of saturation. Okay, as the saturation is getting worse, yeah, it's getting more and more saturated, the value of XS is actually reducing, as we can see in this region here. Yeah. This is where the saturation region already started, and as we can see that the value of XS is drops. Therefore, the value of XS for a given problem, yeah, should be estimated at the approx. Okay, the final test, which is the third test, is done if you want to determine the value of the armature resistance, or RA. Yeah? And the test is pretty simple. We can just simply apply a DC voltage to a stationary machine's winding, and then we measure the current. Yeah? So the resistance can be then calculated by dividing the voltage by the current. Okay. There is a slight inaccuracy here because in the real practice, this machine is dealing with AC voltage, it's not DC, and when we have AC voltage, the actual resistance will be higher, yeah, because of the skin effect. If you imagine this is the cross section of the winding, yeah, or the wire in the windings. When we have AC, it tends to flow near to the skin or near to the surface. So for example like this, yeah? So it will flow in the shaded area, so it's not flowing through the center of the wire, and because of this the resistance will be the effective resistance will be higher, because if we know that resistance is equal to rho L over A, and now the A has been reduced because the center part of the core of the wire is not used, so the effective area has been reduced, and this will cause the resistance to increase. However, again, the error is normally negligible.